Uh, oh, yeah, reviewing content. I want to just go back a bit and review caches because I think I did not explain them well enough when we did our architecture lecture 2 weeks ago. So basically what a cache is they're little pieces of memory very close to the CPU that are very fast and store data that they store data. They're kind of like they're a transparent shim between the CPU and the RAM, so that if you access a value a lot, it'll get moved into that cache and that access will be faster, is the basic idea. So if, for example, I had this program and I was just step through it. So if we have this move line right here, right, that'll just copy the number 20 into A1. So, and then this line here will copy 10 into A0. And those will be addresses in memory. That's how we're going to treat these numbers. So if we were to load T0 with the data that's stored at address A0, so A0 is 10. So the CPU would go to its first level of cache and say, hey, do you have any data from address 10? And this level of cache does not have any data in it, as you can see. So this cache is going to say, hold on a second, let me check and let me find that data to the CPU. And it's going to hop into here, hop to the level 2 cache and says, do you have anything at address 10? And the level 2 cache isn't going to have anything at address 10. And it's going to hop over to the level 3 cache and say, do you have anything from address 10? And level 3 cache doesn't have it. So level 3 cache goes to main memory and retrieves the value that's at address 10. And say the value, so the value stored at address 10 is 5, right? So it's going to load 10:5 into, so the data at address 10 is 5 into this cache, and it's going to get pulled into here, right? Because the level 2 cache has level 3 cache what was here, and it's going to get pulled into here, and it's going to get pulled into here. So now the computer would move on. But if I ran this load instruction again, then it would say, okay, let's see, we would say, okay, level 1 cache, do you have any data for address 10? And the level 1 cache would say, yes, I do. I have a level, the data stored at address 10 is a 5, right? And instead of going all the way up this hierarchy, now you just have that data almost instantly accessible to the processor, right? So the caches are these little transparent blocks that sit between memory and the CPU to try to speed up accesses. So data that you access a lot will get pulled into the cache by these loads, and accessing it will always be faster. Now, say you add T0 and you add T0 to 100, and then you store that result back. Now, if you store that result back, you can also speed up that operation because you can just store that 105 here, and instead of storing it all the way back to main memory. So now you've updated the value here, and if you were to load it again, load the data at that address again, it would say, okay, I remember this is 105. Now, of course, the level 2 cache and the level 3 cache and main memory don't know about this yet. So what happens if I were to load? So let's say the level 1 cache can only hold one value. If I load something else at address, if I load T1 with the thing in address A1, and memory of 20, A1 is 20, is equal to 13. Does anyone have any guesses as to what will happen? So there's only one slot in L1, and none of these have address 20. Does anyone want to make a guess as what's going to happen? Okay. So what will happen is the CPU will check here, and this cache doesn't have it. So the level 2 cache will say, okay, I'm going to check the level 3 cache. And the level 3 cache doesn't have it, so it gets it from main memory, and it says, 20 is 13. And then that'll get propagated down here. And the level 1 cache will say, okay, I got to pull that into my cache. Okay, Pablo asked, so real quick, just so this will remember that it hadn't pushed that 105 back to the other two caches, and it will pull this in, but before it pulls this in, it will write back the 105 and overwrite the values in the previous caches, and it'll send a 105 to main memory. Okay, Pablo asked, why wouldn't we have a very large amount of caches with a small CPU to just rank stuff depending on how often we access it? Why is the CPU even necessary? So the CPU is the part that does the computation. So the CPU is the part that can do the additions and the subtractions, right? And the caches are just data stores. They're basically arrays. So you can think of it as a lot like mail, right? So, your main memory is like a big, you're some company, right? And people send you letters and they ask you to do things, and then you go do those things and return the results. So they might send you a letter and say, hi, please make me a garage, right? They might send you a letter that instructs you to do this thing. They would send this letter, and it would go to some big USPS distribution center warehouse, right? And then they would send that letter to, your local post office. And then it goes to your company, and you send out a garage by mail. It's a very large post office, right? So your local post office has the fastest access to you, right? So if you want to operate on things that are nearby, like, so if they send, please make me a garage, and they happen to be, the local post office is kind of like your first level of caching, right? So if you send a value to your local post office and someone else in the area wants it really fast, or you say, actually, post office, can I get that back and adjust the answer? You can do that really fast. If you send it all the way out to the warehouse, then it's going to take longer. So the CPU is basically, that's the part doing the computation. The level 1 cache and the level 2 cache and the level 3 cache just store the results, right? So basically, the point of these caches is, like, if you're operating on a matrix, like a really big matrix, the matrix, right, if it fits in the level 1 cache, that's great. And every time you need to, like, if you're doing like a matrix multiplication, and every time you access an element and it's in the level 1 cache, you can do that really, really fast. That's awesome. If you make the matrix a little bit bigger, and now it only fits in the level 2 cache, then every time you access a matrix element, it takes a lot longer, right? So you might notice this when you're writing code, and you might have already noticed this, is that as you increase the problem size, like, the time it takes to compute kind of grows linearly, and then there are just steps, right? And those steps are usually where your problem can't fit in the level of cache closest to your processor. So now the problem has to be now the problem's stuck in level 2, and all your accesses take 5 times longer, all of them. And if you did the homework, you saw exactly this behavior on the add arrays question, where if you decrease the cache size by just a little bit, all your speed up on your second run went away. So you ran your program once, and that pulled all of the elements that you were adding into the first level of cache, right? And then you run your program again, and all those elements are already in the cache. And then the second time you run the program, you don't have to spend as much time waiting for data because it's very close to the CPU. But if you make your cache a little bit smaller and those elements don't fit in the cache anymore, then the elements have to stay in memory, and you have to pull them both times. I hope if that kind of makes sense, because I know it's confusing to a lot. I think Aditya was actually a little bit confused about how caches work, and I wanted to highlight them because they're optimizing. If you ever see someone say, we optimize memory access patterns, people like to say memory access patterns, basically like what order do we access variables in memory? This is what they mean. They just, they optimize how quickly they optimize basically the order that they access stuff to try to keep as much of the problem inside the cache as possible. And a lot of the speed up from like large linear algebra libraries like NumPy over what you would write yourself are just because they thought really hard about how to keep all the values that they need to do like a matrix multiplication in cache. That's where most of the speed up comes from. Okay, so talking about where the rest of that speed up comes from is talking about threading. So last week we talked about SIMD, so where you take multiple values, 1, 2, 3, 4, and you run a single operation. So single instruction, multiple data on all of those things. So like multiply all of these by 2. Today we're going to be talking about a more kind of general form of that type of thing, where instead of doing SIMD, we're doing what is often jokingly called MIMD, which is multiple instruction, multiple data. No one actually calls it that other than when people are making jokes comparing it to SIMD. But basically, if you take, so you have your processor, right? What if, and you have memory, and sometimes, you might have one program running that's doing some machine learning, and another program running that's, running your web browser, and then another program running that's, playing Spotify, right? And those all seem like they're running at the same time. And in often cases, they actually are running at the same time. And the way you accomplish this is by having one big block of memory, one memory address space, and then you have multiple processing units. So like the things that can do the addition, the multiplication, the division, all the actual like thinking parts of a computation. You have multiple CPUs attached to the same piece of memory. So, this processor might be operating on an array over here. And this processor might be, incrementing this number, just, making it larger, right? And they can be, these are both values in memory, and they can access them at the same time. And this process can say, okay, say this process has a little slot in memory that it uses, and every time it, does an operation on this array, it checks that slot. So it's the slot, and it checks that slot, and it adds that value to the array or something, right? This processor might, go and say, okay, I can talk to this processor by setting this value in memory to some other number, and the program running on this processor knows that, that if some other processor changes this value in memory to a different number, that it's supposed to do something else, like it's supposed to exit, or it's supposed to print a result or something, right? So you have so basically the processor is like the one in the homework. You just jam a bunch of those onto basic. So we talked about memory. It's a lot like a list, right? We just have a bunch of things that can concurrently, at the same time, access and write values to that list. And they can all do operations at the same time. They can all, like do some math or, play your music or whatever, right? And that sounds really great, because that sounds like a great way. Yeah, it's exactly like Christian said. It's exactly like collaborating on a Google Doc in a sense, right? So like everyone's working on the same thing, and for the most part, it all works fine. But I love this analogy, Christian. I'm going to steal this from you. So what happens if you and your friend both start to try working on the same section, right? Especially if there's some lag there. most of you probably know that everything just goes to shit. So, depending on whose results get to Google faster, someone's text might overwrite someone else's text, or you're trying to format something and then someone 3 pages up is adding a bunch of stuff and it's just smushing it all down. It's a real pain. I'm sure you're all aware of this. A lot of that comes because these operations are inherently non-deterministic. Like the CPU has some things that some instructions that it runs that usually take like 10 milliseconds, but sometimes might take 100 milliseconds. And basically, we'll show this when I open a notebook to do an example, but you basically can't predict. These aren't synchronized by default in any nice way. It's all kind of all over the place. It's a bit random. So this leads to a couple hazards when you're writing multi-threaded programs that can really bite you. And we're going to talk about 2 of the main ones. And this is not an exhaustive list of all the hazards, but a lot of different hazards are manifestations of these. So say you have 2 programs running at the same time, and they're operating on some values in memory. We have the values over here. So right now we're just using the value at 10, which is stored in A1. So the A1 stores the address 10. And at the address 10, we have, the number 10. And we want to implement the following function, but we want to parallelize it so maybe it'll run faster. We want to say, x is equal to x plus 1 squared, right? And what we're hoping is that we can have one thread compute the addition and one thread compute the power, and things will run faster. So we have this thread over here, program A, and this thread over here, program B, and they're both running at about the same time. So if all this works and program A runs first, and it runs T0, so it loads A1 into T0, and then it adds T0 to 1, then stores T0 back into here. So this will now be I wish I had an eraser, easy access to an eraser. There we go. So now this will be an 11. Then program B, we get lucky, and program B runs strictly, everything in program B runs after program A. And the program B says, okay, now I'm going to load this result into T0, multiply it by itself, and that's like 100 and what's 11 times 11?
121. Yeah,
121. Okay. It'll multiply 11 by 11, store the result back in A1, and we have 121, right? That was awesome. It is actually not faster than doing it in series because we have to do it in series anyways, but it works. Now, what if we got unlucky and program B started running a couple milliseconds before program A? So now we're starting with 10, and it's going to multiply it. So we're going to get, so this one's going to double it, right? And we're going to get 100, right? And then this is going to run, it's going to add 1 to it, and we're going to get 101. Different results. Okay, so it's clearly non-deterministic. But say we're fine with this. We're fine with getting 121 or 101, because those seem like the only reasonable answers here, right? Now, what if program A runs at approximately the exact same time as program B? So program A runs. It loads, so we start with 10. It loads T0 into A1. And so now T0 is going to be 10. So T0 is equal to 10. Okay. Now say program B started just a nanosecond afterwards, and it goes and it loads at almost exactly the same time. It loads T0 into A1. Now we have now we have T0 is A1, and this T0 is 10. And we're right here in this program. Now this runs, and this runs, and we have T0 is 100, and T0 is 11 here. And then this store runs, and it stores 100 into address 10. And then this store runs. Now, in an ideal world, this should store, we would want 100, and we would want like 121, right? But because this loaded the value from A1 before this program had a chance to store it back, this is going to store back an 11. And it's going to overwrite this. And it's going to be as if program B never ran. So this is what's called a race condition. And the way you solve this is you have a lock. So a lock is basically says, okay, I'm going to lock the value in A1, and I'm going to lock the value in A1. And then we're both going to unlock A1. And we're going to unlock A1. Okay, so now we can be a little bit more predictable about what's going to happen. So this program is going to strictly return, x plus 1 squared or x squared plus 1. Oh, shit. Plus 1. Okay, there's a 1 here. Sorry, that's the exit button for this tablet. So what a lock does, so I'm asserting that this is what it does. And how that works is the lock is a magic instruction inside the CPU that says, okay, if I lock A1 and then any other processor core tries to lock A1, we're just going to, the second processor core is just going to wait at that lock until I run the unlock. And this is how we solve a race. So we still have a race condition here, right? X plus 1, you get x plus 1 squared or x squared plus 1. But now we only have two possible results instead of we only have two possible results here instead of 4 possible results like we had before. So if this one runs slightly before and it gets its lock, then this program hits here. And if you were to run the stop without the locks and times, can we calculate? Probably we can get 121, 101, or 11. Yeah, so there's actually a third answer, which is 100, which is if without the locks, the third answer is 100, and that's if this one runs slightly before. Sorry, fourth answer. So we have 4 separate answers, right? So our original program could get 101, 11, or 121, right? It could get all 4 of these. We can't explicitly compute the probability of these things. A good guess would be 1/4 for each, but it's going to depend on a lot, like how they were launched and stuff. But a good guess is 1/4. Sometimes race conditions like this don't show up until you run things really fast. So for example, the Linux kernel has a driver for floppy disks. And as you all probably know, floppy disks are really old storage mediums that are really slow. They're really, really slow. And people run virtualization software on like Microsoft Azure. And they'll virtualize a floppy disk. And instead of that floppy disk working at 10 kilobits per second, that floppy disk will run at hundreds of megabits per second. And when you run a floppy disk at 100 megabits per second, race conditions that never showed up when you're running these slow floppy disks, because you just got lucky, and the time that, say if this program took way longer to get here and this program took way shorter to get here, and you ran them at about the same time, you're almost always going to get the same answer, right? But the floppy disk driver had a race condition that happened because this floppy disk driver was written in 1991. No one was expecting, 100 megabits per second, floppy disks pushing gigabytes of data because that's ridiculous. And now we're sitting here in 2018 and someone has to patch the floppy disk driver on the Linux kernel because it's causing crashes in enterprise workloads. It's a floppy disk driver, but they're still using it because they're still virtualizing their software. So race conditions, this is one of the big issues is, there might be a 1/4 probability of getting each of these, but you might also have this one has a probability of 0.9999, and it never shows up in your testing that you get any of these results. And then runtime, your customer makes a little change, or your customer runs this program, and now you get the wrong result. And that really sucks because it's almost impossible to debug. Basically, the moral of this story is that parallel programming is hard. Another type of thing. So we have locks now. So now we can make more predictable behavior, and we can actually we could add some more like locks to make sure that this program runs before this one or vice versa, right? Like it doesn't seem that hard to do. You can just they can both lock some. They can lock some special. They can lock like the address 20 even though they don't use it. And then that will cause one to wait for the other. But because they can communicate, right? So they can, you can try to synchronize. But now that you have these locks and you're like, okay, I can solve all my problems. Easy. We run into another hazard, which are called deadlocks. So say we have this function. We say we want to do, T0 plus T0. Oh, sorry. A1 is equal to, we want this to do this operation. The thing at A1 is equal to the thing at A2, or that's even more confusing. Just X is equal to Y times X plus Y, right? So okay, so we insert our locks here to make this work. And we have lock T0 here, or sorry, lock A1 here. And these, so here we have X is the thing stored in A1, which is going to be 5, and Y is the thing stored in A2, which is like a 10, right? And we have lock A1, lock A2, lock A1, sorry, lock A2, lock A1. And then we have unlock A1, unlock A2, and we have unlock down here for like the same unlock. Okay. Could anyone guess a hazard that you might get if you ran this code and both programs hit this line at exactly the same time? Can anyone guess a hazard here?
If you lock both, then it can't do anything. So it just gets stuck.
Yeah, exactly. So this program locks A2, and this program locks A1. And then this program tries to lock A2, and this program tries to lock A1. So this program is waiting for this program to unlock A1, and this program is waiting for this program to unlock A2, right? And now you're just waiting at this line, and your program's never going to go anywhere. That's exactly right. So the way you would solve this is you'd have like a third kind of fake value that you don't need, but you add here a lock A3 and a lock A3, right? And then neither of these can get into starting these other locks until you pass this lock A3, right? And it's just kind of like a faux value that you lock to make sure that you do stuff in the right order. So this is really hard. As you can see, there's a lot of pitfalls here, and they're not obvious. And sometimes you run code 100 times and it works, and then you send it to someone else and it just crashes spectacularly. People spend their whole lives writing better algorithms to handle concurrency in ways that are faster but still work, or trying to prove that their code works properly. Here's the whole field. And you probably don't want to deal with any of this. And because of that, Python has what's called a global interpreter lock. So anytime that you access any value in Python, there is a single lock for the whole Python interpreter, for your whole program. You have to acquire that lock, make the changes, and then release that lock. So that means that basically there's like some big lock at the start of your program, in the Python interpreter somewhere. And anytime you do anything, you acquire this lock. And anytime you do, so you can see why this might be a problem for performance, because if you try to multi-thread code, if program A is trying to access a variable A, and program B is trying to access a variable B, right? That's fine. They can access these two different variables concurrently. But the way Python works, in order to prevent things like deadlocks, there's only a single lock. So program A has to acquire that lock, and program B has to acquire that lock. And that way you avoid deadlocks, right? Because this program is guaranteed to unlock this lock at some time because it's going to finish with its computation. This program won't lock anything else because there's nothing else to lock until you acquire this big lock. And that solves your problem. It also makes your code slower. So we can do multi-threaded code in Python with a library called multiprocessing. And it kind of works. And if you're really, really careful about how you use your variables, you can actually write code that's faster. Most of the time, your code's not going to be faster. It's going to be slower. And there's basically no real way to get around that. So over here, I've got a function, right? And from the multiprocessing library, one of the things I'm importing is process. And process is it's a function basically that lets you build, or it's technically a class, but you can think of it like a function, right? And it lets you say, okay, I'm going to say I want to run this function. So we wrote this function that just takes one argument and says hi from that argument, right? So I'm going to run my target for this process, which is going to run on a separate core potentially, right? At the same time as my program's running, is going to be target is equal to this function up here. So target is equal to func. And we're going to pass it one argument, args is equal to I. And because we're doing a tuple, but it's one element, we have to add a comma here. That's like not a huge issue if that doesn't make sense. And then we're going to, so we're making 30 processes, right? With arguments 0 through 29. We're storing them in a list. But we haven't actually started these threads yet. We're calling multiple concurrent processes threads, right? So if we do thread to start them, so for each, if we go through all the threads and we do thread dot start, right? That will start that thread. Okay, so let's do that. Awesome, that looks great. Right? So let's print so if we actually run this, we'll notice that this will start all the threads and they'll all print. But this last line here actually runs before all the threads complete. And if you're writing this in a Python file and the program exited when, so if your Python program closes when you hit the end of the cell, which it doesn't in Jupyter, but it would in a file, then this last thread is actually not going to print its output. It's just going to get killed, right? Because all of your threads have a parent thread that is the main thread that this cell is running in. So what we're going to do is before we exit, we're going to go through each thread and we're going to call the function thread.join. And that's basically just means that we want to wait until that thread has finished. So now, I spelled thread wrong. So now, hi from the main thread runs after all of the other threads have completed. And one thing I want you to notice here is that for the most part, all of these threads run in order. But if you look closely, you'll notice that there's actually a few of them that didn't run in order. So hi from 8, it went, hi from 1, 2, 3, 4, 5, and then it ran 8, 9, 7, 10, 6. That doesn't really seem like the right order. And that's because these threads are non-deterministic. Most of the time, they run in order, or mostly in order. Can you guys still see me?
Yeah, you're good.
Okay, sorry, okay. So most of the time these threads run in order or mostly in order, but here you can see this thread ran a little bit before, thread 6, which was started after it. And that's because my computer is doing other things in the background and it's interrupting the Python process to run other things. And this thread happened to be on a core that got interrupted. I guess it's because I'm running Zoom. When I tested this before class, it was always in order. Now it's not, because I guess Zoom uses a lot of cores and a lot of processing power. I hadn't thought of that. And we can amplify this if we do, if we use there's a Python function which just tells the program to wait for a little bit. If we do time.sleep random.random, right? They're really out of order, right? So you can see that these things really are running concurrently. So say we want to try to use this to increase the speed of a function. So for example, basic thing is we have this function square, right? And we want to basically square each element of a list D. So if we run this, it'll square each element, and it'll take 129 milliseconds, approximately. If we run it again, it might take a different time, but it's about 120, 130, 110 milliseconds, somewhere in that range, right? Python has a nice little function called pool. So if we do so part of the multiprocessing library is this class pool. So if we do p equals pool, so it takes a little time to create a thread. So we're going to create a pool of threads. So we have this thing called a thread pool. And what we can do is we can say, okay, we can use this pool to map. We can use this pool. So Python has a map function, right? And a map function does is it takes one function and it applies it to each element of a list, right? Pool has a map function too, but if we do p.map, it will run it'll run that function on multiple different cores. So in this case, 16 different threads, and that function will run on multiple different things. So you would expect this to be faster, right? So if we do p.map square, comma, d, right? We time it, right? This should run faster, right? It doesn't. It runs twice as slow. And a big part of why this occurs is because of the global interpreter lock, right? Because basically they have these threads have to synchronize and talk to each other, and they have to. The problem has to get divided up into the threads, and if all of these threads have to lock onto all of the threads have to lock onto this list to access it. They're actually all going to access it serially. One way we can increase the performance here is Pool has an argument called block size. And we set block size to some reasonably large number. Oh wait, I want IMAP. Oh, chunk size. We can run things a little bit faster. But it's still not as so we're approaching the performance here. It's still not as good. One way you can break this global interpreter lock is by compiling stuff to NumPy, compiling stuff to machine code and accessing the values there. And the global interpreter lock doesn't apply to values that number jits, so that it doesn't apply to number values like we talked in the last lecture. So one thing you'll note is, say if we do like d array is equal to np.array d, you'll notice that NumPy is a lot faster. At squaring things. Part of that is SIMD, part of that is parallelization, and part of that is part of that, and because it's in a NumPy array, it can parallelize stuff in a way that you can't really do in Python. And we can actually approach the performance of this pretty well, and in some cases beat it with stuff that we're making with Numba. So we talked about the vectorize function last week. NumPy, so one of the arguments that I didn't mention, but if we do vectorize, right, there's a argument to the vectorize decorator, target. So the argument is target. And if we set target equal to CPU, right, then it will function that's the default way vectorize operates. So if we have square vec, which is the same thing, then I'm going to just copy this over from my notes because we're running out of time. If we have square vec, which squares a number, right? We set target equal to CPU, and we time that. Sorry. Okay. If we time that, we can actually, we get somewhere approximating how fast NumPy goes. All right. So NumPy is, pretty fast. We're actually a little bit faster. That's pretty good. What we can also do is we can parallelize this. So if we do target equals parallel, then we can explicitly parallelize this function. And let's give that a try. And we'll notice we get an error. This is because the Numba is a little bit dumb and it can't figure out what types stuff is operating on dynamically when we run in parallel mode. And the way you solve this is you just tell it where our function operates on 64-bit integers and it returns 64-bit integers. So it takes a 64-bit integer argument and it returns a 64-bit integer argument. When we publish the homework, I'll have more documentation on this because I took a little bit longer with the slides than I expected to. And if you run this, it actually goes slower, right? So that's a little bit strange. And that's because you have to do some of the same type of synchronization that you have to do when you do this with. So one is the thing is NumPy is actually already parallelized, but the other thing is, in fact, you have to do some of the same type of synchronization. And you don't really have to, but the library is not smart enough to figure it out. One of the things you can do to improve this is you spend a lot of time spinning off threads. If you increase the size of your problem, wait, sorry, I got ahead of myself. one of the things you can do to speed things up is you explicitly parallelize this operation. So ngit parallel is equal to true, right? So ngit was the to jit something, which is different from vectorize. And if we have, the square function, yeah, multiprocessing doesn't work super well, unfortunately. And we make some return array. And we go for I in. So we have range normally. If we are working with number parallel functions, we have a new range function, which is p range, which is a parallel range. We iterate over the if we iterate over all the numbers and we set we don't need this. We set x of I. This is going to be an easier demo. Yeah, I'm going to talk more about this next week probably. But if we basically, so we do the same function, but we explicitly parallelize it and we square stuff. And then we return x. Then if we actually run this, and I pick time it.
So we are out of time, but this shouldn't take like a minute more, right?
Yeah. So if we run this, we notice that this is actually slightly faster than our square vec problem, but still a little bit slower than NumPy. And this is true for and actually if we change parallel equal to false, so it just runs serially, we actually get a speed up. And that's kind of disappointing. But if we increase our, because you would expect the parallel version to be faster, but in fact, right, so right now it's taking 909 microseconds, and we run it parallel, it takes 10.8 microseconds. That's not what we want. If we parallelize it, so this is because our problem size is still pretty small. And if we increase our problem size, then the overhead of creating multiple threads actually decreases. So if we increase our problem size with a larger array, parallel equals true should take about 8.67 milliseconds. If we turn it off, fingers crossed here, live demos never work, and it's still faster. Let's add a couple zeros there. Okay, 73.6 milliseconds with a really big array. If we turn parallel off, please work. Yeah, it takes a little bit longer, right? And so one good thing to remember, well, before you parallelize your code, is your problem size large enough to take advantage of this speed increase? And the answer is actually often no. But if you parallelize a large enough problem, then your parallel code is going to scale better than your scalar code, and you can get more of a speed up, right? And you'll notice here it says CPU time user 904 milliseconds, wall time 71.4 milliseconds. Is there a general rule of thumb about large enough? Usually the best, not really. If you're operating on like a megabyte or 2 of data, then writing parallel code starts to become worth it. But the better rule of thumb is, can my problem be parallelized easily? And then does my problem take more than 100 milliseconds? If the answer is your problem can be parallelized easily and it takes more than 100 milliseconds, then that's probably about a crossover point. If it takes less than 100 milliseconds, then the overhead of creating threads, which is going to be on the order of about 100 milliseconds, might not be worth it to you. So you'll notice that the CPU time here is actually higher than the CPU time up here, or sorry, the CPU time here is higher than what was given as the wall time. So the wall time is like total time elapsed from start to beginning. The user time is the sum of the time used on all processors, right? So if we change this to parallel equals false, they're going to be about equal. So if we change parallel equals false, the wall time and the total times up here are about equal. If we change them to true, then it's actually about 8 times bigger because I have 8 cores on here. Does data type affect its ability to be parallelized? Usually no, because all of your code is going to have these, all of your cores have the same type of like unit, like the same type of units. Like they have like, the same type of multipliers. They handle the data types just as well. The exception to that is if you have floating point numbers, like a lot of floating point numbers. On a lot of processors, they'll turn on the cores that support floating point numbers, and those cores make a lot of heat. And if those little parts of the cores are on in every core, then your CPU overall will heat up, and you'll lose a lot of that speed up because it will run the whole thing slower in order to accommodate the heat created by all the extra computation, if that kind of makes sense. Basically, if you run stuff on all the cores, you can generate more heat, and that will slow your whole system down. That was the question Sarah asked. All right. Sorry, this went a little bit over. I will stay around for another couple minutes to answer more questions, but I don't want to take any more of your time. I think I'm going to talk a little bit more about this on next week because we cover a lot of the same things. So yeah,